even before we saw what are eigenvalues and eigenvectors, what did we discuss? Sorry? No, let's skip that. Let's no. 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 What is this? Yes. So we saw earlier that the representation of vectors is basis dependent. Right? In fact, not just vectors, the representation of uh, linear transformations like this from Rn to Rn is also basis dependent. Right? And if A is the representation of some linear transformation in the standard basis, its corresponding representation in the X basis, assuming um, X is a set of vectors that forms a basis for Rn. Okay, how do you get the corresponding representation of this linear transformation A in the X basis? This is in the standard basis. And how do we know? And what is X? X here. It's an n cross n matrix, no? Whose columns are the basis vectors for basis vectors of what? Of the X basis. Okay? And how do we know this matrix is invertible? Right, because the columns form a basis. That means for Rn, that means they have to be full rank. I mean, the matrix has to be full rank. And this is called similarity transformation. And Ax and A are what? Are called similar matrices. Sorry, what is the question? You tell me. You tell me. Yes. Why would it be? So this is in the standard basis, and we want to convert it into the X basis. So is this correct? So you're saying it has to be like this, right? Correct. Why is it like that? That's correct. It is like this. Why is it like that? This, right? This takes stuff in. If you give it stuff in X, it'll give you in the standard basis. This only works with the standard basis. So this gives standard basis. Yes, that is correct. You are right. Okay. Okay. All right. What did we talk about? And then we talked about eigen vectors and eigenvalues. What are these? So if you have a matrix A or a linear transformation from Rn to Rn that is represented by some square matrix A, what is when do you say something is an eigenvector or an eigen? X, where X belongs to Rn, or in fact we said in this particular case, let's Cn and lambda is some complex number, and not equal to 0. Okay. If this is the case, then what is x and what is lambda? If x satisfies this, what is x? X is an eigen vector of A, and what is lambda? Eigenvalue associated with x, and this pair is called the. And how do we find out the eigenvalues and eigenvectors for a matrix A? Right. So you take this matrix A, and then you solve for this equation. And if you do this, you will get a polynomial in lambda, and this will be an n order polynomial. That means there will be n roots, n complex roots. That means there are n eigenvalues, and they can be repeated. Okay. And what do you do after you? So you get n. So if you do this, you'll get lambda 1, lambda 2, lambda n. What do you do after this? Yeah. Right. Then you do. Then you for each eigenvalue, you solve for this and find an xi that satisfies this equation. Okay. And if you do that, then you get your lambda I xi for I1 to n. This is where we stop. That means if you have a matrix A that belongs to Cn, then there are n eigenvalues I1, that means n, and there are n corresponding eigenvectors. Okay. So if that is the case, then I can write stuff like this, right? Equals lambda 1 is 1, lambda 2 is 2, it's n equals lambda n xn. Now, if you simply collect all your x's, okay, in a matrix, there are n eigenvectors. So let's say I collect all of them like this into a matrix. Okay. A multiplied by a set of columns, this will simply be equal to what? What will be the, if you multiply the matrix A by this matrix, I'll call that matrix X. Okay. Can I multiply those two? What is the size of this? N cross n. What is the size of this? Hey, hold on. What is the size of this matrix? 1 cross n, is it? Hey, these are vectors now, right? This is n cross n. So you can multiply. If you multiply, you'll get an n cross n matrix. What will you get here? What will be the first column? So what, lambda 1 x1, is it? Okay. Why will it be lambda 1 x1? That's correct. But why will it be lambda 1 x1? Hey, hold on. But okay. What is the okay? If again go back to this, the column view. What is the first column of AB? Sorry, what is the first column of C? Sorry, ith row, is it? What is the first column of C? Okay, that's all. No, I mean the ith column of C only depends on the ith column of B and your matrix A. That means the first column is simply A times x1. Second column is a times x2, but a times x1 is lambda 1 x1. Lambda n xn. But here we have a matrix whose first column is some scalar times x1, second column is some scalar times x2. That means I can write it as some x multiplied by a matrix like this, but you have to tell me what this matrix will be. What will be the elements of this matrix? This we know, this is this. What will be the elements of this matrix? What will be the first column of this matrix? First column, you have to tell me n numbers. All zeros in there. Why all zeros? Because the first column only contains lambda times all of this is 0. What about the second column? And then this will all be zeros. This will all be zeros. What about the last column? Right? That means, turns out if you take A and multiply it by X, you get X multiplied by a diagonal matrix. Okay, and this is a diagonal matrix formed by the n eigenvalues. Okay, is X invertible? Is X in this case in? Okay, for now we don't know. Let's say if X is invertible, okay, then you can write A as X times okay only if this condition is satisfied. That means X inverse is X inverse does exist. Okay, and this is the second matrix decomposition that we see in this class, which is called the eigen decomposition. What is the first one we saw? QR. We saw A equals QR. This is the second one. Is that a similarity transformation? This one. Or if you write it the other way around. So if A is this, then what is lambda? If A is this, what is lambda? Are A and lambda similar matrices now? Yes, right. It does look like a similarity transformation, right? So in fact, they are. So lambda and A are similar. But what do similar matrices, what does it mean when we say two matrices are similar? Same what? No, not same representation. They represent the same um, linear transformation, but in two different bases. Okay, and the special thing about the eigen decomposition, or when you switch between the standard basis, which is the representation of this linear transformation, whose representation, okay, in the standard basis, the representation of some linear transformation is matrix A. Instead of working with the standard basis, if you work with the eigenvector basis, because we've assumed that X is invertible, that means there is a full set of eigenvectors. That means my eigenvectors x1, x2, xn form a basis for Cn. Okay, if you have a full set of eigenvectors, it means there is an eigenvector basis. Okay. If you have a basis like that, then the corresponding representation of this matrix A is simply this diagonal matrix lambda. Okay. And the interesting thing about this is your linear transformation becomes very simple in the eigenvector basis, because if you have a diagonal matrix, right? Diagonal matrices are very simple matrices compared to matrices that are not diagonal. Okay, and what is the geometric operation that is? So we said that if you have a matrix A, and if you matrix A which maps from say Rn to Rn. So if I take a vector x from Rn, and then I apply the linear transformation A, I get another vector y, which is Ax. What does the linear transformation do to this vector? What geometric operations does it perform on this vector to produce y? Right. There are three things that matrix generally does, right? There is scaling, there is rotation, and there is maybe reflection. That is for any general matrix. What if your matrix was diagonal? All zeros here and here. What is it doing then? Yeah, it essentially only does scaling. So, if you have any general linear transformation whose representation is a standard basis A, which involves any combination of all these different operations, if the matrix has a full set of eigenvectors, okay, then the corresponding representation of the linear transformation in the eigenvector basis is a diagonal matrix. That means in the eigenbasis, all you're doing is you're taking the vector, uh, you're taking its representation in the eigenvector basis, and you're simply stretching the components along the different eigenvectors. Okay, let's see an example of that. Okay. So the advantage of this decomposition, when you can decompose it like that, is that you can represent a complex linear transformation into a fairly simple form. Now, imagine, let's say we are dealing with R2. We talked about how we can visualize what a linear transformation does, right? If you take a unit square located whose bottom left corner is located at the origin, and then we look at what this linear transformation A does to each of these three vectors, 1, 2, and 3, and of course 0, 0 gets mapped to 0, 0. And then the change in shape tells us what kind of operation is being done. Okay. Now, let's say we have a linear transformation, or let's say we have a matrix A. That is, what are the eigenvalues of this matrix? 2, 1. Okay. Can you give me two eigenvectors for this? Or what are the eigenvectors for this? Anything. If you do it, you will find out. Uh, is it anything? No, I am wrong. It's E1, E2. You can verify that. So one way to think about this, what A is doing to this matrix is, instead of working well, in this case, it turns out the eigenvector basis is also the standard basis. Okay. So what your matrix is essentially doing is it takes this figure, right? It stretches this figure along the x-axis by a factor of 2, and then it stretches it along the other axis, the x2 axis, by a factor of 1 to give you this. Okay. So if you apply A to this figure, this is what happens. That means if you have any arbitrary vector now, you take its corresponding component, x1 component, you take its corresponding x2 component, you stretch the x2 component by a factor of 2, you leave the x2, sorry, you stretch the x1 component by a factor of 2, you don't do, well, you stretch it by a factor of 1, and then so this vector would get mapped to something like this, because you've simply stretched the x1 component by a factor of 2. Well, this was a fairly simple matrix. I mean, we already started with the diagonal matrix, right? But we'll look at something a little bit more complex. I need this. Here? Okay. Here. If the corresponding eigen decomposition of this matrix is this. I 2001 I, because your eigenvector matrix X is simply I. So one way to think about, so when I said that the representation of a complex linear transformation becomes simple in the eigenvector basis, what I mean is this. You switch from the standard basis to the eigenvector basis. In this case, the eigenvector basis and the standard basis are the same, right? You take any, I mean, if you have a vector, right? You first decompose this into the corresponding components of this vector along the eigenvector basis. So in this case, because eigenvector basis is the standard basis, the components are this one. Let's say this is some vector b. This is b1, some scalar, the corresponding vector here is b2. And then you apply this diagonal matrix. This matrix simply tells you, you take the first component, scale it by a factor of 2. You take the second component, scale it by a factor of 1. So if I take this and I scale it by a factor of 2, then I get this. I take this, scale it by a factor of 1. That will give me this vector. Okay. So this was b1. Let's say this is b2. Sorry, not this was b1. This was 2 times b1. This is b2. And this, since the scaling is 1, this remains the same. That means my new vector is this. Right? B gets mapped. This will be a b. Okay. Again, this is trivial because we started with this. Okay. Now instead, let's say we start with some a, and then you can tell me what this matrix will be. I'm writing the corresponding eigen decomposition. You can tell me what you get for a. So you can think of this as x lambda x inverse. What is a? I think it will give me, just verify. What is it? Is it correct? -1, is it? Okay. Otherwise, this is okay now. Okay. Now let's assume we started with this. Okay. And then I ask you, what is this actually doing? Okay. Looking at this, it's not immediately clear. Okay. But that's because this is in the standard base. Okay. Now I ask you, okay, if I take this unit square, okay, this is 1 0, this is 0 1, and this is 1 1, and I ask you, what is this doing? Okay, what is this matrix doing? Right? It's not clear what happens here. But if we switch to the eigenvector basis, okay, uh, where is eigenvectors here? Eigenvectors. Uh, no, no, hold on. Is it 1 minus 1 1 1 or 1 1 minus 1 1? So that will be this vector, right? That's this vector. That's 1 1. And then the other vector is -1 1. That is here. That's this. I mean, I chose this so that this is the eigenvectors actually form orthogonal basis. But if instead if I chose this to be 1 by root 2 and this to be 1 by root 2, then I have an orthonormal basis. So this is my eigenvector 1, eigenvector 2. Okay, even though I don't know, it's not easy for me to figure out what geometric operation is going here. Instead of looking at this square in the standard basis, if I simply look at it in the eigenvector basis, that's essentially you rotating this. Okay, in the eigenvector basis, I know exactly what happens to the square, or in the eigenvector basis, this won't be a square, but a square rotated by an angle of 45 degrees. No, for example, if this was your reference, for somebody using this as the reference, this square would look like this to them. Okay, assuming for whatever reference you're using, the first basis vector for you is always horizontal, and the second one is orthogonal and stuff like that. Okay, so for this person who's working with the eigenvector basis, it looks like this. And the geometric operation that is represented by this lambda is very simple for this person, right? You take the component of whatever vector you have along the first basis vector and stretch it by a factor of 3. That means this person would take this figure and then stretch this by, this is 1, by a factor of 3 without doing anything to the other axis. They're only affect, because it's diagonal, that means you're only impacting the first component. So nothing would change along this axis. So you'd simply stretch it out to get this. Okay, that's the effect of the first eigenvalue. Second one, that's the second eigenvector. You're not doing anything. That means this is it. So if you apply this linear transformation in the eigenvector basis, this is what you get. But this is still in the eigenvector basis. What would this be in the corresponding standard basis? Well, going from here to here, all I had to do was rotate it by 45 degrees, okay, by clockwise 45 degrees. After I apply this transformation, to go back from my eigenvector basis to the standard basis, I do the rotation by -45. That means the corresponding operation here would simply be, or the corresponding representation in the standard basis would simply be okay. You can verify this. I would recommend you go and write a program, MATLAB or Python, and then find out what happens to the square when you apply this transformation. You will see something like this. Okay. It would have been hard to get to this figure by simply looking at this. But the moment you decomposed it like this, it's a lot easier to see what is going. Okay. Now, what would happen to this if this had been 3? Well, You first stretch this out by a factor of 3. You now stretch this out by a factor of 3. And it turns out that will simply be, the whole thing is stretched uniformly. To put this. Or 3. Well, you take this, first one you squish, this thing gets squished. So you essentially have a line, and then you stretch that line out by a factor of 3. So this one, so what would happen to this? What would happen to the square? Straight where? Along this? Is the question clear? This is your uh, this is your linear transformation in the eigenvector basis. This is the standard basis. You got to the, let me remove this. This is this. First one, you take this, you squish. If you squish it, then you get this line. And then you scale it by a factor of 3. Now, what will be the corresponding representation here? Right. So this square would get squished, would become this 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 line. Okay? Because this also tells you another thing. Whenever you have an eigenvalue that's 0, your matrix loses rank. Okay. So if you multiply this out, you will find that this matrix has rank of 1. Okay. I hope that's clear now, right? What the use of doing eigen decomposition when you can decompose it. Before we conclude, there are two more things I want to discuss, which is basically eigen decomposition of symmetric matrices. Symmetric matrices are very useful matrices that we often come across in applications. And it turns out they do have some special properties when it comes to eigenvectors and eigenvalues. What is a symmetric matrix? Rn to Rn. When do we say a matrix is symmetric? Or if it's in Cn, so if this was then H. If this is satisfied, then you say the matrix is symmetric, right? It turns out there are, when these three things you can remember for now, but these are easy to show. That when you have a symmetric matrix, all eigenvalues are real. You don't get complex eigenvalues. It'll always come out to be a real number, positive, negative, or 0. And two, the eigenvectors can always be chosen to be or chosen to form an orthonormal basis. It's not that they will always be orthogonal to each other, the eigenvectors. It's just that you can choose them to be orthonormal. Okay. For example, is this matrix symmetric? This is symmetric. The eigenvectors turned out to be E1, E2. This forms an orthonormal basis. The previous matrix that we looked at, 2, -1, -1, 2. What were the eigenvectors? They were orthogonal to each other, 1, 1, and 1, -1. Okay. All right. So this, just remember this for now. Okay. And then finally, Now, so well, when we when I wrote this down, I said if x is invertible. Okay. Now let's see when you cannot write. So it turns out you cannot write any n cross n matrix like this. Uh, there are cases where you cannot write it. So you have a this. What are the eigenvalues of this matrix? Lambda 1 plus just 1, right? Both of them will be same. What are the corresponding eigenvectors? Okay, let's write that down. So you do that by first substituting lambda 1 is 1. So this will be 1, 2, 0, 1 minus 1, 0, 0, 1. This will be what is an eigenvector for this? Huh? Yeah, okay, 1, 0. That's an eigenvector. For lambda 1 equals 1. Lambda 2 is also equal to 1. But we only have one eigenvector. Okay. So whenever this happens, right, that you don't have a full set of eigenvectors that you can obtain for a matrix, then it turns out you cannot express it in this form. Okay. What you can do, again, take this without any proof, is you can't write it in this. You cannot diagonalize A anymore. But what you can do is block diagonalize it. You cannot write A equals x lambda in x inverse. What you can do is write it like this. Some matrix P, some J, P inverse. Okay. And this uh, form of writing is it's called the Jordan form. Okay. And this matrix J is not diagonal anymore, but it is block diagonal. Okay. That means J would have this form J1, J2, J K, and this is all 0. And each of these matrices, each of these is a matrix. And of course, K is less than N. And each of these matrices corresponds to a specific eigenvalue, lambda 1, lambda 2, lambda k. And the and each of these is called a Jordan block. Okay? And a Jordan block for Ji, which corresponds to the eigenvalue lambda I, simply it's like this. You have lambda I along the diagonal, and then the diagonal just above the main diagonal, it's all 1, and it's 0, 0. Okay, this is a general form. Any n cross n matrix can be written like this. Okay, if you have a full set of eigen values, then you can write it like this. And this is still true. It's just that your Jordan block now becomes a matrix like this. So you can think of this a diagonal matrix like this as a Jordan form with where each of these entries is an individual scalar. And to see when this happens, again, we said it happens when we don't have a full set of eigenvectors. And that happens only when your eigenvalues repeat. If the eigenvalues don't repeat, then you don't. So for example, if you have a matrix with n distinct eigenvalues, then no problem. You can always diagonalize it. But the moment you have repeating eigenvalues, you can get into trouble. Okay. So when you have repeat, let's say you have a matrix A, n cross n. Let's say it has k eigenvalues. Okay. And let's say lambda 2 repeats. Okay. There are multiple eigenvalues whose value is lambda 2. Okay. And the number of times an eigenvalue repeats, that's called its algebraic multiplicity. Right? So here, the algebraic multiplicity of lambda 1 would be 2. Okay. That's am. Okay. And the number of eigenvectors that you can identify for a repeating eigenvalue or for any eigenvalue is called the geometric. Okay. Whenever gm equals am, then there is no problem. You can always diagonalize. Whereas here, see, here am was 2. What is gm? You could only find one eigenvector. So here, gm was 1. Gm is lower than am. That means you cannot diagonalize it anymore. The best you can do is write it in this form. Okay? Whenever you do have a unique set of eigenvalues, then am is 1, gm is 1. You can diagonalize it. But I've removed it. You can write a equals x lambda x inverse. Okay? That means in this particular case, the best we can do for a is write it like this. So a can be written as some p. Lambda is 1. Lambda 1 is 1. So 1 1 0 1 inverse. Is that clear? See, for people that are familiar with um, uh, linear time invariant systems, um, your eigenvalues, we will see this in the next, not the next lecture, but the lecture after. Eigenvalues correspond to the poles of the system. And whenever you have a situation where you have repeating poles like this, that's when you can get into trouble. Okay. So your Jordan form is essentially when you have two repeating poles at a particular location. Okay, all right. That's all I wanted to say about eigenvalues and eigenvectors. There is one more slide in the lectures where you um, I basically ask you to write the Jordan form. So if you have an eigenvector, let's say we have a matrix A with say 4 eigenvalues or 2 eigenvalues, let's say lambda 1 equals 1, lambda 2 equals 2, and let's say 1 has the algebraic multiplicity of 2 and geometric multiplicity of 2, and then 2 has am of 1 and gm of 1. What would be the corresponding J matrix here? Well, in both cases, am equals gm, so there is no problem. You can diagonalize the whole thing. Right? So if you have am, if you have lambda 1 repeating twice, then you have 1 1. Am equals gm. That means this is simply 0 0. Lambda 2 repeats just once, so there is no problem. Whatever repeats only once, there is no issue. So it will simply be 2. So this would be your J matrix. But instead, this is 1. What would change? How would this change? Right. Now, this will become J1, and J1 will simply be 1. Okay. What about this? What will be the size of this matrix? Lambda 1 has AM of 2, GM of 1. Lambda 2 has AM of 3 and GM of 1. It will be 5 cross 5 because there are 5 eigenvalues, 2 ones and 3 twos. Okay. And what will be the elements here? What will be J1? 1, 1, 1, 0. That's J1. This will be your J2. Okay. What about this? The geometric multiplicity was 2. Well, this would disappear. That's all. Okay. All right. Okay. That's all I wanted to discuss about eigenvalues and eigenvectors. Are there any questions so far? Otherwise, we'll move to the next module. No? Okay. I'll move this. Okay. All right. So the next topic we'll look at is another important topic. Which is on positive definite. Okay. Okay. We know that if you have a vector from Rn, what do we know for sure about this? If I have a vector from Rn and I take x transpose x, yeah, it's a scalar. Okay, what else do I know? That's correct. It's a scalar. Right. So okay, you can compute it as like this. I equals 1 to n. Okay. All right. So what else do I know based on this? It's a sum of square of a set of scalars. What does that mean? So what does it imply? Can I say this? Well, if x value is 0, I've written greater than or equal to 0. So this is correct. So this is for sure true, right? So whenever a vector, you do this, you know this is true. If it's from Cn, then you know this is true. Okay. In fact, this is true also because this is the second norm, the square of the second. And norms are always non-zero, uh, except for when the vector itself is 0. Okay. All right. So we know this is true. But let's say we have a matrix A that maps from Rn to Rn. What can we say about something like this? Well, first of all, what do I get if when I multiply this? When I get when I write down an expression like this, what is the resultant of this, or the size of the resultant of this? Do I get a matrix? Do I get a vector? Do I get a scalar? Get a matrix? What is the size of the matrix? N cross n is n. Are you guessing or did you do the calculation? Yeah, it's a scalar. What you get is, well, here, this is a column vector, inner product, standard inner product with a column vector, get a scalar. Okay. If it's a scalar, then I can ask, okay, what can we say about the sign of the scalar? It turns out the sign of this is something useful. It tells us something about the matrix itself. Okay? So I could ask, what, what is the sign of this? Right? And whenever you write this expression is called the quadratic form. Okay? Well, let's take some examples for the matrix A. Let's say A was equal to, then what can you say about, first of all, let's say A was a 2 cross 2 matrix. Well, tell me what is this first? 2 cross 2? So you have 2, 0, 0, 4 multiplied by x1 is 2. What do I get when I multiply this out? Yeah. Can I say something about the scalar now? Whether it will always be positive, or you cannot say if it will be positive or negative. This will always be greater than or equal to 0. What if it was like this? Okay, will it always be positive? If A was minus 2, 0, 0, minus 4, what is x transpose AX? Is this always positive? It's always less than or equal to 0, right? This is always positive, this is negative. What about this? What will I get? What will be the corresponding quadratic form? Can I say anything about the sign of this? Well, yes, you cannot say. It depending on the value of x1 and x2, this is sometimes positive, sometimes 0, and sometimes negative. Right? So here we are not sure. The sign is not sure. But the previous two cases, we are always sure about the sign. Okay. Well, I've chosen diagonal matrices to make our life simpler. But if I have an arbitrary matrix, okay, you'll get a corresponding quadratic form like this. If you do, that's yeah. And we are interested in knowing, is this always greater than or equal to 0? Is this true? Okay. And whenever you have a matrix A, okay, and we will only, okay, whenever we have a matrix A that satisfies this condition, okay, where x transpose AX is always greater than or equal to 0, when x is not equal to 0, okay, then we say A is a positive definite matrix. Okay? Okay. But say we know this, x transpose A is greater than or equal to 0. That is all we know. Okay. I've removed this condition. Okay. Because when x is 0, this is obviously 0. We know that this is always satisfied. That means even if x is not 0, for some x's, uh, this quadratic form could be equal to 0. But for other values of x, it simply gives you a positive value. Then we say A is positive semi-definite. Now, we can similarly talk about, if I've said positive definite and positive semi-definite, obviously there is also negative definite and negative semi-definite. Then you say A is negative definite if minus A is positive definite, and similarly A is negative semi-definite if minus A is uh, positive semi-definite. Okay, so we only have to talk about positive definite, because negative definites you simply talk about minus A instead of I. It turns out these, I mean, this is a useful idea uh, because we come across matrices that satisfy this property often in applications. For example, when we're talking about when A represents an inertia matrix, okay, then we find that A is well, A has to be positive definite, or in some cases maybe it can be positive semi-definite when we're talking about covariance matrices, right? And when we are dealing with optimization problems, we are interested in knowing whether or not some matrix A associated with the function that we are interested in is positive definite or not. Okay? That tells us whether or not the function has a minimum. Okay, so in optimization, this comes across, and again various other applications. I mean, it is important enough that this topic itself is useful to study. Okay. Now the question is, okay, how do we find out if something is positive definite or not? Okay. Yeah. Yes, it is. Yeah, it'll turn out if your matrix A is positive definite whenever when all the eigenvalues are positive. Okay. If one of them is 0, then it's semi-definite. If it's negative, then you don't know. If all of them are negative, then it's positive, or it's negative definite. Right? But if you have both positive and negative values, then you don't know whether or not. Now, for example, so if you have a matrix where for some values of x it's positive and some values of x it's negative, then of course none of these applies. It need not. So this is not exclusive. You can have matrices that are neither of these. Okay. Okay. Now, the place where this comes up, we have only 2 minutes. Okay. And I said this idea of positive definiteness comes across when we do optimization. Uh, we are familiar with some. For example, let's say we have a function x that's square. Okay? And I ask, okay, does this function have a minimum? Okay? How would you find that out based on what you know from what we've learned from calculus? Well, you say, well, for it to have a minimum, then this has to be 0. Well, x is a scalar. But that's not enough. What is an additional condition that you have to have for the function to have a minimum? Because this is satisfied by both what? By maximum and minimum. Should be what? Oh, negative, is it? Greater than 0. Okay. So we know that if that these two conditions have to be satisfied for any function f of x to have a minimum. For example, what is the curve of this graph? Well, it looks like this. What is the first derivative? And where is the minimum? It's at 0. Okay. What is the first derivative at this point? X equals 0. It's 0. What is the second derivative? 2. So it's positive. So it has a minimum. So this seems simple enough. Okay. What if we then now move on to not a univariate function of a single variable, but function of two variables, which looks like a bowl, or not necessarily a bowl, but where you have a function which is a function of two variables. Okay? And for this case, we are interested in knowing, well, where is the minima, or does it have a minimum? Okay? Right. So in this case, what you do is instead of you look at the partial derivatives, the corresponding condition condition would be the partial derivative of f with respect to x1 and x2 has to be 0. But again, that only tells you that it's a stationary point, right, where the slope is 0. It does not tell you whether it's a maximum, minima, saddle point, and all that. The corresponding condition for this, it turns out, depends on a matrix. Now, let's function like this. I leave today's class here. Can you write this? Okay. Can you write this in this expression in a quadratic form? That means you have to choose your A appropriately so that it comes out to this expression. You can do that as an exercise today. We'll meet tomorrow. Are there any questions so far? Okay, all right. Is it possible for us to shift one of our classes Thursday evenings to Friday mornings? Are you guys here?